Welcome to Vector Calculus. In this video, I'm going to give a bit of an overview of the big ideas, the big themes that we're going to see in vector calculus. And actually, this video is the first video in an entire playlist on vector calculus that corresponds to about the first third of my course as a professor at the University of Victoria. So I encourage you to check out the rest of the playlist. The link to that is down in the description. The first big object of vector calculus is something called a vector field, and these are both vector fields. You can either have a two-dimensional vector field or a three-dimensional vector field. Well, what is a vector field? It says, at any point in space, I'm going to put a little vector there. A vector is something that has a direction and a magnitude. For example, gravity is a vector field. At any point out in space, if I take a particle and I release it from rest, it's going to move under the force of gravity. And so at any point, there's kind of like a little arrow there that says, well, what direction is the force of gravity pulling this particular particle, and how strong is it? The longer the arrow, the stronger the force. Same thing for the electric field or the magnetic field. For example, you might have heard of the magnetosphere around the surface of the Earth. You know, when you have a compass and it tells you a direction, well, that is aligned with the magnetic field. But you also have just vector fields, like, for example, a moving current of water in a river. It says at any point there is a velocity vector that tells you where is the water moving at that particular point and how fast is it moving, how long is the vector. So vector fields are everywhere in physics and math and engineering and so on. Okay, so that's vector fields, but I also talk about a couple other objects. The first of those being curves. A curve is some path in space. As time goes on, I move along a path. This path is a three-dimensional one, but it could be two-dimensional as well. And I've kept the third dimension plotted, even though my path is two-dimensional, because after we ask the most basic questions, like, I don't know, what's the arc length of your curve? You could imagine a function that lives above your curve, gives a value at any point along your curve. So for example, I could ask the question of the surface area above this curve where I have some height function above the curve. And even if my curve was three-dimensional, I might be interested in some question of having some function that lives in some sense above my curve and try to add everything up. That is the concept of a line integral. So that's curves, but I could also have surfaces. My surfaces might be closed like the sphere, so it really encloses some volume inside of it. Or it could be a surface like this one, where it's got a boundary curve to it. And I could certainly ask questions like, what are the surface area of this? But I also might want to ask, well, what if I had some function assigned at every point along the surface, like the temperature, for example, at every point along the surface? How could I add up all of those and get, for example, an average temperature? Those will be called surface integrals, and we're going to see that too. So curves and surfaces are interesting, but what I'm most interested in is the relationship between curves and surfaces and a vector field. For example, either two-dimensional or three-dimensional, I have my curve or my surface, and I've got a vector field swirling all around it. So what kind of questions can I ask? How do these have some interplay? So one example is called flux, and another is called flow. The idea of flux is, to what degree is the vector field moving out or dispersing across the boundary? That is, to what degree is the vector field aligned with a normal to my curve? Actually, in the example I've used where my vector field is swirling around in a circle and then my curve is also a circle, I don't think any of the arrows are crossing the boundary, and so maybe there's no flux in this example. And then the other thing I might be interested in is this measure of flow. Flow is the opposite. It's the tendency for the vector field to be aligned with the tangents to the curve, as opposed to the normals of the curve. And I might imagine this, for example, if my vector field is a moving surface of water with a velocity at every point, and I paddle around in some path, what is the tendency for my movements to be aligned with the actual underlying currents of my vector field? Am I able to sort of flow along with the underlying currents without having to do any paddling at all? The degree to which that is true is a measure of something we call flow. So those are two-dimensional ways that the fields and the curves could interact, but I have the same basic idea in three dimensions. If I have a surface, and it's got a series of red normal vectors at every single point, I could ask for the yellow vector field, what is the tendency for the vector field to disperse across the surface, what we call the outward flux, and we're going to have a measurement of that. Or if I have a surface with a boundary that's living inside of my vector field, I might ask the question, well, what is the tendency for the vector field to cause a particle to flow around that boundary curve? And How is that related to what's going on the inside of the surface? So those are some big questions that we're going to focus on. Now, vector calculus has some of the most beautiful and powerful theorems in it. Theorems like Green's theorem, Stokes' theorem, and divergence theorem. And these are all about relationships between local properties and global properties. What do I mean by this? A local property is something that happens at every single point. So for example, if I had a vector field, which I didn't plot the actual vectors here, but imagine I did, and imagine that that vector field caused little spinners to spin around at every single point. This is a local property because at any individual point it might be going clockwise or counterclockwise, faster or slower. It's something that's true, this degree of spinning at every single point. And then the question is, how does that relate to a larger global property, like the tendency for a particle to flow around the boundary curve? What's going to be so amazing about vector calculus is that we're going to have these really nice relationships between local properties and global properties. Ways where we can accumulate or add up all of the local properties throughout an entire region and deduce some very important global properties. And these theorems are going to be sort of the triumphant conclusion to our little course on vector calculus. Alright, so I hope that stokes your curiosity about vector calculus a little bit. I'm very much excited to be with you on this journey as you're learning vector calculus. If you would, please do give the video a like for the YouTube algorithm, because I think everybody needs to learn vector calculus, don't you? If you have any questions, do leave them down in the comments. I try to read them, I try to answer as many comments as I can, and we're going to get into the nitty-gritty details in the next video.